আমরা বিসিসের দ্বিতীয় দিনের প্রোগ্রাম তৃতীয় হাফ শুরু করতে যাচ্ছি এবং এখন যিনি এই প্রোগ্রামটা বা চেয়ার সেশন করবেন, মডারেট করবেন, উনি হচ্ছেন ডক্টর অভিজিৎ বেরা, মিদনাপুর কলেজ। স্যার, তাহলে এইটা সেশনটা শুরু করে দিন।
Okay, thank you, sir. Thank you, everyone. Good afternoon, first of all. Actually, we are now in the third session of today's program, and in this session, there is two participants will be delivering their talk. One is Savitri Rai, and the second one is Arjun Kumar Limbo. I have already seen Arjun is present here, but I do see here Ms. Savitri Rai still till now. So, sir, if it is not problem, then maybe we can start with Mr. Arjun Kumar Limbo. You have any problem, Arjun?
No, sir.
Okay, fine. So we will have 15 minutes for the talk session, and the five minutes will be for the discussion. So you may start, and I wish you good luck. Okay.
Thank you, sir. Hello, am I visible?
Yeah, you are audible, but not visible yet.
Sir, am I visible now?
Till now, no. Yeah, now it's coming, maybe. Yeah, it's coming. Yes.
Good afternoon, everyone present out here. I am Arjun Kumar Limbo from NBBGC Tadung, Gangtok. Today, I am here to present a review on the topic elucidating the mechanism of working of SNO2 gas sensor using combined operando UV visible Raman.
Mr. Arjun,
Yes,
if you
sir.
don't mind, I just interrupting you. So can you please make the screen is full? I mean, you just put click here in the downstream to make it a full screen.
Sir,
As a
I have made
presenting.
the screen full.
No, I mean, if you may, okay, wait a moment. I can show you. So here you can see in the bottom line where you are increasing the size of the page, there's a symbol, U shape. Please click here. You can come to the right side in the bottom in the right side. Yeah, go down a little bit more, little bit left. Yeah, this one. Click this one.
Yes, sir, I've clicked it.
No, not that it's coming.
Is it full screen, sir? No?
No, not yet. Maybe it is coming. Wait a moment. Can you click again? Right. I mean, in your side, it is full screen, right?
Yes, sir.
Oh, but it is not coming here. Anyway, no problem. Just continue.
So here's my plan of talk: introduction and the experimental observation, result and discussion, and acknowledgement. So
Sorry, Arjun, your slide is not coming right now. It is not changing. Can you please stop it and again start?
Okay, sir.
Stop the presentation and start again. Somehow it is stuck. Yeah, do it again. And click there where I told you right now. Click in the slideshow.
Orion, if the net is strong, you on your video, face-to-face interaction more better.
But sir, but first is slide is not working properly. So maybe we can fix first the slide and then video will be the second problem, second option. But still the slide is not working well, I'd say.
Sir, am I not visible right now?
Yeah, I mean, you are visible, but the problem is the screen is not making full screen. And when you are changing the slide, it is not coming. So that is the problem.
So,
I don't know. It's an issue. Yeah. Can you click here again? It is from beginning, the top corner, left side, top corner. Yeah.
yes, sir.
Oh, but it is not coming here in our side. Okay. I don't know. Maybe just continue by like this way. It's coming. It was coming. Just do it again. And just wait a little bit. Your internet maybe is not so strong.
Yeah, sir. Maybe internet is little slow right now.
Yeah.
So, sir, can I present my slide like this?
Yeah, do it.
So, introduction. Sir, can I start?
Yeah, you can start. No problem.
Okay, sir. Okay, sir. So, introduction. The SNO2 is most widely used metal oxide gas sensor material, which is based on the concentration of oxygen vacancy of the metal oxide and the nature of absorbate present in the gas environment and the gas phase composition. In this particular article, the author have used ethanol gas sensing for to directly correlate it with the presence of oxygen vacancies and the surface species, particularly in acetate and hydroxy group. In this method, the operando approach has been used using IR, Raman, and UV visible spectroscopy. So, experimental observation for this SNO2 gas sensor. This here graph depicts the reflectance spectra of SNO2 gas sensor at 325 degrees Celsius at various gas environment. Here, this insight show the experimental setup for multispectroscopy, and this legend shows the experimental order. And from, as you can see from this graph, the reflectance has been drastically decreases as the gas environment has been changed from oxidizing air to the reducing gas environment, ethanol and nitrogen. So here in this graph, as you can see that this green line shows the green spectra shows the nitrogen after the reducing agent has been introduced to the gas environment, and the nitrogen was introduced again. The reflectance has been raised again, but it was not up to the original level. This is caused due to the presence of oxygen vacancies in the metal oxide surface. So we can say that the reflectance in the visible in the is the indicator of level of reduction in SNO2 gas sensor. Next slide. This figure 2 shows the Raman spectra for visible Raman spectra for SNO2 for different gas composition at 190 degrees Celsius and 325 degrees Celsius. In 190 degrees Celsius, here the black spectral line shows the Raman spectra, and the Raman feature are only seen in the 3631 centimeter inverse, which is due to the presence of hydroxy group. And switching upon to the ethanol and nitrogen, we no longer see this Raman feature over here in red line, and instead we see the peak in 2937 centimeter inverse, which depicts the acetate group presence and due to the absorption of ethanol with the hydroxy group. And switching to the air in 190 degrees Celsius, there is a decrease in the intensity at 2937 centimeter inverse, and new Raman band is appeared at 2887 centimeter inverse and 2966 centimeter inverse. And these two combine forms the formate species, which is found due to the partial decomposition of acetate group. And upon switching upon the air in 190 degrees Celsius, ethanol and air, there is no longer the Raman feature has been seen. Only the acetate group is present at the 29937 centimeter. So, and moving to the higher temperature at 325 degrees Celsius, here is here is the Raman features, but are weak Raman features. This is due to the higher temperature and the surface processes in the SNO2 gas sensor is fast. And in air, you can see that here is a present of hydroxy group in 3631 centimeter inverse, and upon switching to the ethanol and air, we can see also the acetate group present. So this Raman spectra provides information on the presence of absorbate and hydroxy group. Next slide. Moving to the next slide. This figure depicts the simultaneous measurement of sensor resistance, reflectance, Raman band intensity, and FTIR spectra. So from this graph, this white area depicts the nitrogen, and this dash line of red depicts the ethanol, and this gray area here shows the air concentration. So switching from the nitrogen to the ethanol in here, we can see that this black line drops drastically, and this black line represents the resistance, and it depicts the decrease in resistance. And as you can see, this blue dot has also been decreases, which shows the reflectance. And as we see in the Raman band intensity, there is a formation of acetate group here. The intensity of acetate band has been increased, and upon switching to the again nitrogen, the resistance has slightly been increased, and the reflectance has also been slightly increased. And here, if we see closely here in the Raman intensity band, the acetate intensity has been slightly decreases, and this is caused due to the formation of CO2 in the CO2 gas in the surface, which has been detected by IR intensity. So, and if we change the environment to the air, then the resistance has been increased again, and the reflectance has also been increased. And in the Raman intensity band, we can see that the acetate has been decreases, and the new line of green has been formed, which is known as formate. And here, moving on to the higher temperature, so that we can remove all present absorbate from the surface, we can see the higher peak in the carbon dioxide here. So which is the sharp peak that shows the carbon dioxide is decomposed in the air. And in this process, the resistance has also increased drastically, and the gas sensor has been set to the initial value. And switching to the ethanol environment, the resistance again has been decreased, and the reflectance has also been decreased. And in IR, it has been seen that the carbon carbon band has been highly increased as compared to 190 degrees Celsius. And in Raman spectroscopy, there is no Raman feature or Raman band has been observed. And reducing the temperature to 325 degrees Celsius and from nitrogen, switching from here nitrogen to ethanol, there is a again decrease in the resistance and also in the reflectance. And in Raman band, there is a formation of new band which is known as carbon band and which is assigned as DNG band. And here also acetaldehyde group, which is presented by this green line, is also been increased. So overall, this graph can detect the absorbate present in the concentration where the Raman detection limit detection is limited. Excuse me. And moving to the next slide, result and discussion. So our sensor response can be explained by the electrical surface potential, which is from the result of ionization of gas molecules, or by the change of oxygen stoichiometry by the variation of number of surface oxygen vacancy, and increase in the acetate concentration and oxygen vacancy leads to the decrease in resistance. And as a result, this demonstrated result, this operando Raman UV visible spectroscopy are highly sensitive to structural change of metal oxide gas sensor material. Acknowledgement. I would like to extend my gratitude to BASIS for providing this platform, and I would also like to extend my gratitude to Dr. Omnath Little for his guidance. Thank you, sir.
Thank you, Arjun, for your nice presentation. So you are a PhD student, right? Or you are just submitting?
No, sir. I'm PG student.
Oh, okay. You are a MSc student. Yeah, it's really excellent.
Yes.
So you did a nice work. I mean, during this semester's time. So, okay. So maybe we can have some few questions which can our guest can be ask you some questions. So please, if you have some questions, please ask Arjun. I may have one question, Arjun. Are you
Yes, sir.
listening? Okay.
Yes,
So
sir.
did you when the experiment actually you performed in your lab, or you just survey the system for this talk presentation?
Sir, I have just read this paper and
Okay.
gone some language. That's
Okay.
it.
So you did not do any experiment, right? You didn't perform any
No, sir.
experiment for this system. Okay.
No,
fine.
sir.
Okay. Okay. So if you have no questions from audience, so I may again thank you, Arjun, for nice presentation or your efforts. So maybe we can again meet in the same type of platform. Best of luck. Thank you.
Thank you, sir. Thank you, sir.
Okay. So our next participant, Savitri, is already here. I have seen her. So if you are ready to present, maybe you will have 15 minutes for the talk, and for the 5 minutes we will discuss about your topic. Okay. Go ahead. It is visible, but your voice is coming very low. Can you say it a little louder? Okay. it's
Good
fine.
afternoon, everyone. Am I audible?
Yes, it is audible. Very nice. Okay.
Good afternoon, everyone. My name is Savitri Rai from Norbadur Bhandari Government College, Sikkim. Today, I'm going to be discussing Fourier transform infrared spectroscopy and Raman spectroscopy of polypropylene and cyclic olefin copolymer blends for qualitative and quantitative analysis. So in this session, I will be covering, this is the abstract. Now in this session, I will be covering the following topics like introduction, then blend preparation, then Fourier transform infrared spectroscopy. Then I'll move on to result obtained from this FTIR. Then I'll move on to Raman spectroscopy, then results of Raman spectroscopy. Then finally, I'll conclude the topic. Firstly, I will move on to introduction. As you can see here on the screen, polypropylene, which is a multi-purpose thermoplastic. It has a characteristics like excellent rigidity, outstanding fatigue resistance, superior chemical resistance, and it is a good steam barrier. And this is the molecular structure of polypropylene. And cyclic olefin copolymer is an amorphous engineering plastic, and it has the characteristics like superior transparency, high class transition temperature, and it has a good heat resistance and chemical resistance. And this is the molecular structure of the COC. When these two polymers are blended, they are blended using a technique called melt mixing technique using co-rotating twin screw extruder. And this blend has a positive impact in case of the mechanical and thermal properties. This blended form also leads to the development of the novel material, which has a capable applications in packaging, optical and medical sectors. So for qualitative and quantitative analysis of this polymer blend, FTIR and Raman spectroscopy techniques were used. Next slide. The intention of this work were to access IR spectral and Raman spectral data of PP and COC blends, and to analyze the uniformity of blending and determine the blend composition. Now we move on to how polymer blends are prepared. At first, the COC is dried for 3 hours. In vacuum oven. Then that dried COC is mixed with the PP pellets. Then the mixture will be blended by using a technique called melt blending techniques using a co-rotating twin screw extruder. And they will be blended in the ratio 1:100, 100:0, 90:10, and so on. Then the extruded strands, the extruded strands were, the screw spin will be maintained at 200 RPM, and the temperature of the barrel inside the feed zone will be maintained at 180 degrees Celsius, and at metering and die zone, it will be maintained at 270 degrees Celsius. The extruded strands which comes out of the die zone will be water cooled, air dried, and then pelletized. Then that pellets will be dried and molded into rectangular shaped specimen using injection molding machine. And that injection molding machine will be carried out at cylinder temperature of 280 degrees Celsius. Then injection pressure will be 300 bar, and injection time will be 10 seconds. Now we'll move on to FTIR, or Fourier transform infrared spectroscopy. This is the diagram of the infrared spectroscopy instrumentation. In FTIR, when the IR radiation passes through the sample is here, passes through the sample, some of the radiation will be absorbed by the sample and some will be transmitted through the sample, and that transmitted radiation will be detected by the detector in the form of the interferogram, and that interferogram will be transformed into FTIR spectrum with the help of the Fourier transformation conversion. Then the FTIR spectra were recorded with the help of the Nicolette IS5 FTIR spectrometer in the range of 4,000 to 400 centimeter inverse. Then a total of 32 scans were recorded with resolution of 4 centimeter inverse. Now the results obtained from the FTIR are shown here. This is the IR spectrum of the polypropylene. What we can observe from this spectrum is that we have a absorption peak at 1455 centimeter inverse, which is due to the CH2 symmetric bending vibrations, and at 2838 centimeter inverse, this peak is due to CH2 symmetric stretching vibrations. And we have an absorption peak at 2952 centimeter inverse, which is due to the CH2 symmetric stretching vibrations. Next one. This is the IR spectrum of the COC. What we observe from this spectrum is that we have a absorption peak, which is 1000. The peak at 1017 centimeter is due to the ring deformation of the Norbornene units, and Norbornene units is contained in the COC polymers, and we have a 1596 centimeter peak at the 1596 centimeter inverse. This is also due to the ring deformation of Norbornene units. And we have the absorption peak at 2866 centimeter inverse and 2941 centimeter inverse. This is due to the sp3 hybridization of the carbon symmetric stretching vibration and the asymmetric stretching vibrations respectively. Next slide. This is the IR spectrum of the blend, which is PP and COC blends. This is the IR spectrum of the PP-COC blends. We have an IR peak at 1300 around here, 1375 centimeter. This peak is due to the CH3 symmetric bending vibration. This peak increases as the PP content rises in the blend. And we have the peak absorption peak at 1017. 1017 is somewhere here. 17 centimeter inverse. This is related to the ring deformation vibration of the Norbornene units. This spectrum shows both the characteristics of the COC and PP. And this peak increases if the content of the COC rises in the blend. Now we move on to the Raman spectroscopy. To carry out Raman spectroscopy, measurements, we use a DXR Raman microscope. Then Raman effect occurs when a sample is irradiated by monochromatic light. Then it results in the frequency shift of scattered radiation. This is the scattered radiation. The laser beam of 780 nm was focused on the sample using a objective lens. Then the scattered radiation from the surface of the sample will be directed towards the imaging spectrometer through collection lens, which is not shown here. Then the Raman spectra were recorded by Charles-Koppel device detector. Previous. Oh, wait. Sorry.
Savitri,
Yes, sir.
are you in a laptop?
Yes,
You
sir.
are in a laptop, right?
Yes,
you are in
sir.
a laptop, right? Okay.
Yes, sir.
So you can use your arrow symbol to change the slide.
Yes,
You
sir.
have arrow sign? Yeah.
Yes,
You don't
sir.
need to every time press the next button.
Yes,
Okay.
sir.
You just press the arrow symbol, you will get the next slide.
This one. No? Now, next slide. Now we go on to the results obtained from the Raman spectroscopy. This is the Raman spectrum of the polypropylene. We have observed that the peaks are between the 500 to 1500 centimeter inverse, and this is the gap in between, and we have obtained the peaks from 2600 to 3000. The peaks which have occurred between the 500 to 1500 is due to the CC backbone stretching vibration and CH2 deformation vibration and CH3 deformation vibration. And the peaks which have arisen due to between 2600 to 3000 centimeter inverse is due to the CH2 and CH3 stretching vibrations. The intensities of these peaks, which are between the 500 to 1500 are comparatively less than the peaks which are between the 2600 to 3000 centimeter inverse. The additional bands appeared between the 500 to 1500 are recognized to be the 3-1 helix, which is the normal conformation in isotactic polypropylene polymorphs and mesomorphic phase. We observe the Raman bands at 2885 centimeter inverse and 2953 centimeter inverse, which is due to the CH3 symmetric and asymmetric stretching vibrations. Then the peaks at 1330 centimeter inverse and 1459 centimeter inverse is due to the asymmetric bending vibration of CH3. Now we move on to the Raman spectrum of the COC. The peak at 932 centimeter inverse is due to the ring vibration of COC molecules, and we even observe the sharp peak at 1416 centimeter inverse, which is due to the presence of orthorhombic crystal structure in polyethylene.
Savitri, your time is up actually. You may
Yes, sir.
start your time is actually up, and you can summarize your presentation within one slide, please.
Yes, sir. We observe the peak at 2870 centimeter inverse, which is due to the CH2 symmetric stretching vibration, and at 2924 centimeter, this is due to the CH2 asymmetric stretching vibrations. This is the Raman spectrum of the PP-COC blends. In case of the rich PP, in the blends, the intensity at 800 around the out here, 800 centimeter inverse. The peak at 810 centimeter inverse is high as compared to the 842 centimeter inverse. Whereas if the COC is very high in the blend, then the peak at the 810 centimeter will be low as compared to the peak at 842 centimeter inverse. If the content of the COC increases in the blend, then the ring vibration also increases. Now, finally, what we can conclude from this topic is that FTIR spectroscopy and Raman spectroscopy are utilized for detailed study of NEAT COC and PP-COC blends, and the physical properties of the blends are affected by the structures of molecular chains. And addition of COC to PP causes notable changes to the IR and Raman spectrum bands of PP-COC blends. And even the difference in the content of the blends led to the considerable monotonic variations in IR and Raman spectra of PP-COC blends. These are the references. Now, I owe my sincere gratitude towards BASIS for this great opportunity to give oral presentations. I would also be very much grateful to our professor, Dr. Homnath Liutel, for his guidance and support. And thank you each and everyone present here in this session for your precious time and sincere patience.
Okay, thank you, Savitri, for your presentation. Nice presentation. So, if you have any question from the audience, please. Any question from audience? If not, I maybe end with this in the session with one small question to Savitri.
Yes, sir.
Can you please? I mean, you also did not perform any experiment, but you
Yes.
survey the literature and try to make the
Yes.
presentation with the knowledge, right? So,
Yes.
I just want to know one thing from your side. Can you please tell what is the difference between the FTIR and Raman spectroscopy? I mean, why we need to this two-step spectroscopy to understand the property of the material? What is the basic difference between these two?
In case of FTIR spectroscopy helps to detect functional groups and characterize covalent bonding informations, whereas Raman spectroscopy helps us to analyze polymer backbone structures and chain length, ring opening, and conformations like that.
So both are actually the bond, right? So I mean, all are actually the vibrational bond present
Yes,
in
sir.
the molecular chain, or it is in the single molecule. So I mean, if it's not long chain, I mean, if it is not a polymer or whatever, the small molecule. So there we don't need Raman spectroscopy. That you actually mean. So if it is the small molecule, so you understand what I mean? I mean, you are telling that in Raman, you
Yes,
can
sir.
have longer chain or some chain. I mean, some opening of some chain. Then you can detect this kind of from the spectroscopy. But in both cases, what I know actually, so in both spectroscopy, this is giving the information of the bond information.
Yes, sir. In case of IR spectroscopy, the molecule has to be heterogeneous. Whereas in Raman spectroscopy, it can be homogeneous also.
Okay. Yeah. So, okay. So if you have any question, if you don't have any question, then we may end this session by saying thanks to everyone and also the participants, Savitri and Arjun. Thank you.
You want to say something? Raise his hand.
Shubhankar. Yeah.
Yes.
Mr. Shubhankar.
Actually, I want to ask a question. He is doing the experiment, and we know the Fourier transformation. This is actually the theoretical point of view. Scientist Fourier discovered the Fourier law. So, is there any relation between the theoretical Fourier transformation and what done or what you say in the experimental? Can you explain?
I didn't understand.
Savitri, did you get the question?
No, sir.
Okay, I also thought so. Yes, yeah, Mr. Walker, can you please repeat again the question because your talk was a little bit broken that time.
Okay. Actually, Fourier transformation. This is actually comes from the mathematics. There is some expression. So when we come, actually, this is a totally the Fourier transformation is a from the mathematical point of view, and when you go to the experiment, and there is total some different things. So can you correlate the theoretical point of view and the experimental point of view?
Okay. I think
Sir,
this question is a little bit.
I'm unable
Yeah.
to answer this question.
What? Yeah, Savitri. Did you say
Yes, sir.
something?
Sorry, sir. I'm unable to answer that question.
Okay.
Actually, I am a theoretician, so I know the answer, and I just know from your mouth that is the answer.
Yeah, please share. I mean, Dr. Shubhankar, please share because he's now student only, so he's trying to get the knowledge of this and all the things. So that's why you just share this knowledge.
So actually, when this is there is a quantum mechanics. When we go to the quantum mechanics, when we do the quantum dynamics, and after the quantum dynamics, there will be some wave function, and after some time propagation, we get the wave function, and it is transformed to the next form. And when time propagates, the wave function gradually changes. And after Fourier transformation of this autocorrelation function, we get the actual theoretical spectra. And in the we actually try theoretically try to simulate this theoretical spectra with the experimental spectra. So actually there is a relation is that actually when an experimentalist do some experiment, he don't know the details of this theory. He only put some sample to the instrument and get the data. But whatever the total work is done by the experiment, total experiment done by the machine, the total Fourier transformation, whatever may be the mathematics, totally is done by the machine. So the student or the teacher who perform that experiment, they actually do not know the detail of the Fourier transformation, but he actually get the result. But the main thing actually comes from the theory. So if you take some time, go to the Google and search the Fourier transformation, and there you will get that total details of the Fourier transformation. So, okay.
Okay, maybe we can go for the next session. Thank you everyone for your nice presentation. And I'm ending this session with many thanks. Okay, so.
Yeah, and thank you, Dr. Obid Bera, and thank you, Savitri and Arjun, for the nice presentation. And in the next session, moderated by Dr. Alokananda Hajra, Department of Chemistry, Vishwabharati University, and also a renowned person. And moderate this session. I request the Dr. Hajra, please continue the session.
Hello, Kritada. Before that, can I make a quick comment?
Yes, yes.
Yeah, actually, the four students who presented just now, they are just MSc students, and I just thought to encourage them so that they can read this, they can start reading the resource paper. So they are just just reading the material and trying to understand. So sorry for the inconvenience if they could not answer much.
No, sir, there is no problem, sir. Actually, they are studying and they will take time to understand the whole thing. Actually, they are just students.
Yes,
These are not their fault.
Discussion platform.
Yes. This is a
Thank you.
discussion platform. No problem. Okay.
Thank you very much for your encouragement, sir. Thank you.
Yeah, thank you, Priti Ranjan Sahu, for your kind invitation. I welcome all of you to participate in this platform. Also, I thank the organizer, mainly Priti, for organizing this kind of prestigious platform to giving the opportunity to student as well as the researcher. It is really it is really a good thing to organize this kind of seminar, because many students, they can participate in this seminar. Also, I can find a lot of students, they are presenting their works, that is really good, because undergraduate student, postgraduate student, researcher, they are taking part in this seminar. And also I congratulate Priti for organizing this kind of seminar. Anyway, I welcome all of you to take part in this session. In this session, two students they will present. First one is Dr. Abhinandan Das Pradhan, and second one is Devanjan Jana. Abhinandan, are you here?
Yes, sir.
Abhinandan?
Yes, sir.
Yeah, Abhinandan, he the third year student of Bhattar College. He will present today about crystal field theory. As you know, crystal field theory, that is a very important chapter in undergraduate student. He is also undergraduate student. I hope all of you enjoy his lecture. Welcome. I welcome Abhinandan to present your work.
Thank you. Good afternoon, everyone. Myself, Abhinandan Das Pradhan, from Bhattar College, Danton. I am talking about the crystal field theory, that was a subtopic of coordination chemistry. At first, as we can see, the crystal field theory describes the breaking of degeneration of electron orbital state, usually d or f orbitals, due to a static electric field produced by a surrounding charge of distribution. As we can, in 1930, the great physicist Bethe and Van Vleck developed this theory, crystal field theory, short form of CFT. As we know that the covalent bond, and that was formation between the metal and the ligand according to valence bond theory. But in crystal field theory, they assumes that the bond is purely ionic or electrostatic. And next, crystal field theory considered metal as a positive ion and the negative charge as a ligand. Electrostatic force of attraction develop between the central positive ion and the surrounding negative ligand field. From the force of attraction, repulsive force also develop between d electrons of metal and surrounding negative field. Next, we can see the barycenter, that is d orbitals at same energy and presence of ligand. They are excited and got the average energy. So as the ligands approach in the central atom, the repulsion between ligands and the electrons of d orbitals, that is increase. This increase in repulsion destabilizes the d orbitals electron and its energy is increased. Next page we can see that same picture, but the left side picture, that was axis. Axis we can put at the point of ligands. For more clearance of repulsion, we can put the axis at the direction of ligands. Next page, orientation of different orbitals in an octahedral field of 6 ligands. That was 5 d orbitals, and that was dxy, dxz, dz square, dyz, dx square, y square. In the dxy, the dxy, dyz, and dzx have lobes between the axes. Means dxy have the lobes plane of dxy, and the dyz have lobes between the yz, and dxz has the lobes between the xz. And other side, the dx square, y square, or the z square have the perpendicular to the axis of x and y and z. In next page, and this splitting of d orbitals is 2 groups. They are the higher energy group and the lower energy group. Higher energy group from the average energy, that was gx square and z square, as we had denoted by Eg, and the lower energy group, that dxy, dyz, and dzx orbital, that is we denoted by T2G. And the middle has the barycenter, and we can say that average energy. The energy gap different along the ligand in an octahedral complex, and the d orbitals of a central metal ion divided into 2 sets of different energy. The separation in energy is the crystal field splitting energy, and the delta naught is when delta is large, it is energetically more favorable for electrons to occupy the lower set of orbitals. When the delta naught is greater than p, a strong field ligand, then there will come the low spin complex, and the delta naught less than to p means weak field ligand, then they got the high spin. Next, definition of both. Low spin complex is that high spin complexes contain unpaired electrons, whereas low spin complexes tend to contain paired electrons. These are called spin states of complexes. We can determine this state using crystal field theory and ligand field theory. Next, we can see crystal field splitting in tetrahedral field. In the tetrahedral crystal, the field these orbitals imply same T2G and Eg sets of orbital as does the octahedral crystal field. Here, the same thing as we see before, that dx square y square as the higher energy, and the dx square y square, dz square as the higher energy, and the dxy xz and dyz as the lower energy. In the next page, crystal field splitting in tetragonal or square planar complex. If the two trans ligand in an octahedral complex are either chemically different from the other four, then different distance from the metal, then the other four, the result is a tetragonally distorted octahedral complex. There is a large energy separation between the dz square orbital and the dxz and the dyz orbitals, meaning that crystal field splitting energy is large. We can find that the square planar complexes have the greatest crystal field splitting energy compared to all the other complexes. Next page, bipyramidal splitting in trigonal bipyramidal complexes. In trigonal bipyramidal geometry, the three ligands lie along the corners of a trigonal at the angle of 120. As you can see the picture, that the angle between the every ligands at 120 degree is forming the pyramid base in xy plane. The two ligands perpendicular to the base triangle along z axis. Thank you.
Abhinandan, are you finished?
Yes, sir.
Okay. Your presentation is really excellent. You nicely explain the CFT and also the LFT. So now the platform is open to all the participants. I think some students they can ask. You will be happy to answer. Platform is open to all. Abhinandan. Hello. Hello.
Hello, sorry, sir, for some technical issues. Okay, sir.
Yeah, I just wish to know. So, could you explain the color of aqueous copper sulfate? Abhinandan?
Color of aqueous copper sulfate.
Yeah, I think color of aqueous copper sulfate is blue, right?
Yes.
So, how can we explain this one? So, you can explain by LFT or CFT.
No, sir, not available.
Hello.
Sorry, sir, I cannot explain that.
Okay, it's okay. I want to know anything that is not relevant to your lecture, but it could be explained. So, are you third year student, right?
Yes, sir.
Yeah, that presentation is really good, but that is also good opportunity for you because you are undergraduate student. Still, you are presenting one book chapter. That is really good. Your just slide are also good. I saw your slide. That is also really good.
Thank you, sir.
Anyway, I think your presentation is over. Now I welcome your friend Devanjan Jana. He is also student from Bhattar College. He is the student of chemistry. Devanjan,
Yes, sir.
are you ready?
Yes, sir.
Okay. So I welcome you to present your work. You will Devanjan will talk about polymer chemistry. He will discuss the polymer chemistry. Platform is yours now.
Thank you, sir. Good afternoon, everyone. I am Devanjan Jana from Bhattar College, Rathod, semester 5, chemistry honors. Today I will discuss about polymers. First, polymers are macromolecules formed by linking together of a large number of small molecules. They are called monomers. The polymers are giant molecules with high molecular masses. For example, the monomer ethylene gets linked with many other ethylene molecules to form polyethylene, or large number of vinyl chloride molecules combine to form polyvinyl chloride. The single repeating unit is called as monomer, and the resultant high molecular weight compound is called as polymer. Then polymer structure. And then classification. Classification, first of all, based on source. There are three types. First is natural. Natural ভেতরে starch, cellulose এবং protein. And then semi-synthetic. Semi-synthetic এর মধ্যে হচ্ছে nitrocellulose. And then synthetic. Synthetic এর হচ্ছে polythene এবং polyvinyl chloride. এরপর the nature of monomer. First, homopolymers. Homopolymers, a polymer containing identical monomers. Example. Then polymers are the compounds of formed by two different small molecules. For example, polystyrene butadiene. One molecule of butadiene combines with one molecule of styrene. The product often acts as a monomer to get the polymer. And third, on the basis of arrangement of monomeric units in polymer. These are named as linear, branched, or cross, three-dimensional structure. Some example of high polymers are rubber, polyethylene cellulose, polyvinyl acetate, etc. Polyethylene may also have branch chains. The vulcanized rubber is the best known example of cross-linked polymers in which SS cross links are joined irregularly. Due to cross-linking, polymer structure becomes three-dimensional cross-link or network polymer. This makes the polymer very hard and rigid. Then the types of bonding. First is linear, second is branched, third is cross-linked, and fourth the network. Four types of bonding. Then, based on atoms, if the main chain of the polymer is of same atoms, it is known as homochain polymers. While if is of different atoms, and it is known as heteropolymer. First example, একই চেনে, they are called homochain polymer, and next is heterochain. Next, copolymer is named as regular or irregular on the basis of arrangement. First example is regular and the next is irregular. And one is linear copolymer. Then, if copolymer chain possesses relatively long sequence of like monomer, it is called as block copolymer, whereas if copolymer possesses branched structures in which the monomer segments are not in same sequence or branch and backbone, it is known as graft copolymers. Based on effect of heat, polymers are two types. One is thermoplastic and one is thermosetting. Polymers are also classified on the basis of configuration of macromolecule known as tacticity of polymers following ways. One is isotactic polymers and one is atactic polymers, and next is syndiotactic polymers. In isotactic, the head to tail configuration in macro two functional groups each iso. In isotactic, all the functional groups lie on the same side of the chain. In atactic polymers, the head to tail configuration is random. The functional groups are arranged randomly. Example, polypropylene. Symbiotic polymers, arranged of side group in alternating fashion, is called symbiotic polymer. Example, Butta Percha. These are example of homoorganic polymers. First is isotactic, second is symbiotic, and third is atactic. Other examples of organic polymers are polysaccharide, proteins, DNA. On the basis of chemical composition, the polymers are also called either organic or inorganic. Generally, in organic polymers, carbon with or without nitrogen, sulfur, oxygen forms the skeleton, while in inorganic, other elements from the skeleton. Example, polyethylene. Polyethylene, RNA, etc. Man-made organic polymers include PVC, PP, PTA, PF, UF, polysters, polyamides, polyurethanes, synthetic rubbers, etc. Inorganic polymers are those in which atoms other than carbon form the skeleton of polymer. Polysiloxanes or polytitoxanes are the example of polymers where side chain may be of organic nature. They are also known as elemento-organic or heteroorganic polymers. Polysilanes are purely inorganic in nature. Other examples of this class are magnesium oxide polymer or hydrogen borons. Next, polymerization. The reactions of monomers to form a polymer is known as polymerization. The polymers are formed mainly by addition polymerization, that is called chain polymerization. Next, condensation polymerization, that is step polymerization. And third is copolymerization. First, addition or chain polymerization. The word chain indicates elongation of carbon skeleton to form a polymer. Generally, such a polymerization involves the link in monomer. The double bond breaks, and as a result, two single bonds on either side of each carbon are formed, and thereby elongation of carbon chain continues. The product of this type of polymerization is exact multiple of monomer number having no byproduct or loss of any molecule. Addition polymerization is undergone by monomers having carbon-carbon linkage. Example, ethylene, vinyl chloride, propylene, butadiene, styrene, etc. The rate of reaction is very high, and the polymerization reaction involves three steps such as initiation, propagation, or branching. And that is the structure. Ethylene has 2 carbon atoms and 4 hydrogen atoms, and the polyethylene lipid structure has 2 carbon atoms and 4 hydrogen atoms. Next, condensation, step polymer. The monomer being certain functional groups such as OH, COOH, NH2, etc. So the tendency to undergo polymerization by the elimination of one molecule of a simply byproduct such as H2O, H1, salt or alcohol, etc. Unlike addition or chain polymerization, polymer loses simple molecules at every combination. As a result, does not have exact multiple number that is condensation polymerization. Hexanidiol acid plus ethanediol, that is transfer, and the product is a polyester and water. Condensation polymerization is undergone by the monomers, which possesses functional groups. Generally, monomers are like acids, amines, alcohols, phenols, carbonyl compounds, etc. This type of polymerization occurs stepwise. Hence, the rate of polymerization is comparatively slow. It depends on kind of catalyst, the temperature, and the time of reaction. Third, copolymerization. It is a joint polymerization of two or more monomers. High molecular weight compounds obtained by copolymerization are called copolymers. For example, butadiene and styrene copolymerizes to give GRS rubber or Buna-S. And that is the structure, butadiene plus styrene, and the product Buna-S. And some example, first is polyethylene. Polyethylene properties. First, it is high density polyethylene, has high tensile strength, high density. It is relatively brittle and has low impact strength. It has low moisture absorption. And low density polyethylene has low density, low tensile strength, less brittle. It has low moisture permeability. Its applications: high density polyethylene is used in products and packaging such as water pipes, toys, detergent bottles. And low density polyethylene is used for both rigid containers and plastic film applications such as plastic bags and film bar. For example, in orthopedic products, in consumer packaging bags, bottles, and liners. Next, polyvinyl chloride, that is called PVC. Properties: it is chemically inert, it is colorless and odorless, it has excellent resistance to water, it is non-inflammable, it is resistant to light and atmospheric oxygen, and it has excellent resistance to aqueous solution, but it is attacked by stronger solvents such as aromatic hydrocarbons, ketone, esters, chlorinated solvents, etc. Applications of PVC: it is used electric conduit pipe, unplasticized polyvinyl chloride for construction, flooring, pipes, water storage tank, covering, cable, window frames, and fascia and weather boarding. Last is Teflon, that is polytetrafluoroethylene. Properties: it has high molecular weight, it has low coefficient of friction, it has low chemical reactivity, it is resistant to water and alcohol, it is harder and stronger than the other polymers. Its application: it is used in containers and pipework for reactive and corrosive chemicals. It is used as an insulting material for motor, transformers, cables, wires, etc. It is used for making gaskets, tank linings, and packings. And it is commonly used as a grab material in surgical interventions. Thank you.
Thank you, Devanjan, for your excellent presentation. You nicely presented the polymer chemistry. So you explain what kind of polymers are and also utility in daily life. So that is really a good chapter for the undergraduate student. Not only undergraduate student, polymer chemistry now is a just a very good. It is excellent things to all about daily lives. So I think platform is open to discussion. All participants can interact with Devanjan. So platform is open to all.
Thank you, sir.
Devanjan, I have one query.
Okay, sir.
So-
See,
So do you have any idea about biodegradable polymer? Biodegradable polymer. Biodegradable polymer. Anyway, that is biodegradable means it could be easily it could be just it will decompose. By bio means basically how of know like enzyme, these kind of things you cannot degrade. That is a common thing. So that is looks like natural polymers. You explain nicely natural polymers, synthetic polymers. That is the one part of this one.
yes, sir.
Okay.
Okay,
So
sir.
in nowadays, a biodegradable polymer, you can see a lot of good bags or these kind of things in a good shopping mall. These are the biodegradable polymers. Anyway, your presentation is very good. You also nicely explained this chapter, and that is very useful to the undergraduate students. Also, Abhinandan and you nicely explained the two good thing in this platform. That is also good opportunity for you because as you are undergraduate student, that is you can nicely explain in this. Just you have used this platform to explain your just your study material. Anyway, I congratulate Devanjan, Abhinandan for their nice presentation. So I think this session is today's session is over. Scientific session is over. I think there is no inquiry for the audience, I think. Okay, Devanjan, thank you very much for your presentation. Also,
Okay, sir.
Abhinandan, he also
Thank
presented
you.
very well. Now, scientific session is over. Preeti, are you here?
Yes, yes.
Yeah, now you can.
Now, thank Dr. Hajra and দেবাঞ্জন এবং অভিনন্দন দিয়েছো এই যে ভয় আমাদের স্টুডেন্ট ভয় করছিল ভীষণ
না তারা ভালো থার্ড ইয়ারের স্টুডেন্ট তারা ভালো মানে ইন্টারঅ্যাক্ট করেছে এই যে প্ল্যাটফর্ম পেয়েছে বলছে এতজনের সামনে দ্যাট ইজ রিয়েলি এনকারেজিং দ্য স্টুডেন্ট অলসো I think their friends also they will take part in this platform.
Now the
অ্যাকচুয়ালি ওরা খুব ভয় পাচ্ছিল আর কি প্রথমে। হ্যাঁ, আমি ওদের একটু মানে এনকারেজ করেছি আর কি বলাতে।
আমি বুঝতে পেরেছি ডক্টর সর্দার আপনি বুঝতে পেরেছি না হলে এই প্ল্যাটফর্মে যতই কিনা থার্ড ইয়ারের স্টুডেন্ট আমাদের সময় আমরা ভাবতে পারতাম না এরকম একটা ওয়েবিনারে আমরা টেক পার্ট করবো ইভেন ওয়েবিনার শব্দটাই ছিল না ইভেন যে সেমিনার ছিল আমাদের সময় ভাবতেই পারতাম না এত সুন্দর করে প্রেজেন্টেশন দেবো তার পিছনে যদি স্যাররা মানে টিচাররা যদি হেল্প না করেন ইটস রিয়েলি ডিফিকাল্ট বাট ইট ইজ রিয়েলি গুড প্র্যাকটিস ফর দেম I also congratulate Kriti and his colleague Dr. Sardar. Really, they are working hard for this seminar. I think many students they will benefit from this seminar.
Actually, this is our teamwork, basis teamwork.
Yeah, I understand. Yeah.
Sujit, Jyotin, Dr. Puyukta Panchoddai, Dr. Makhanlal Nanda Goswami, Dr. Vijit Bera, everyone behind our program and encourage us.
I know because your friends they are really that is a good for the student. I'm saying for undergraduate student also researcher that is really good.
Outside Homenath encourage their student. The first time their team join our program.
Okay.
Homenath, personally thanks, many thanks.
Yes.
Session we are going to the last session. Vote of thanks by Dr. Shubhankar Sardar, Department of Chemistry, Bhattar College, Daton, and also the member of BASIS. Please continue.
Thank you. Now I come to the last part of the session, vote of thanks. First of all, I thank to the convener of this organizing such a fruitful webinar, which is not only important for the students but also for the teachers. Then I thank to Professor Chittaranjan Sinha sir for constantly support the BASIS activities, and then I thank to the other moderators, Dr. Somnath De Pingla College, Dr. Obijit Bera Bindapur College, Dr. Olokananda Hajra sir, Vishwabharati, for their glorious presence in this webinar series and giving their valuable times. Then I want to thank to the speakers, Orno Pal, Nobunita Bera, Miss Rasmi Sharma, Obishek Sharma, Savitri Rai, Arjun Kumar Limbo, and then our student Obinandan Das Pradhan and Devanjan Bera to give their valuable speech to this webinar. Thank you all. Thank you for your participation in this webinar. Hope you all enjoy so much and get rich. Hope you all enjoy much. Here is the end of today's session. We will meet next third day actually of this. That is 9 December at 3 p.m. And let's go to the convener, Dr. Kritiranjan Sahu, for further details of the program. Thank you.
And next third day, our program will be 9th December and will be starting 3 p.m. And fourth, and the link will be provided in your mail and WhatsApp group. All are welcome for the third day. Good afternoon. Goodbye, everybody, for the day. Again, meet 9th December.
Okay, thank you, sir.